Welcome, curious minds and sleepy thinkers. You found a soft place to land where the questions are big and the pace is slow enough not to jolt you out of your pillow cocoon. Tonight, we're going to tiptoe into one of the most mysterious questions ever asked. We will gently explore why we only ever see one face of our lunar companion and what secrets lay on the side that has, for all of human history, remained hidden. But don't worry, we will take it slow. This isn't a race through equations. It's more like floating through a galaxy of ideas with a cup of chamomile tea. We will honor what we know, and perhaps even more so, we will honor the beautiful mysteries that still remain. So let your mind relax, take a deep breath, and let us begin this quiet journey together. Our closest celestial neighbor, the moon, has for all of human memory presented us with a singular, unchanging face. From the earliest fire-lit nights when our ancestors first looked up to the most powerful telescopes of our modern age, we have always seen the same familiar patterns, the same shadows, the same dark plains and bright craters. It is as if the moon is a silent partner in a cosmic dance, perpetually keeping its eyes on us, while its other side remains a mystery forever turned away. This constancy is not a coincidence, nor is it a trick of our own perspective. It is the result of a profound and beautiful phenomenon known as tidal locking. It is a gentle gravitational embrace that unfolded over an immense stretch of cosmic time, a dance so slow and so powerful that it shaped the very rotation of our moon. To truly understand why one side remained a blank page in our history for so long, we must first understand this elegant, patient choreography. Imagine for a moment the early moon spinning wildly and much faster than it does today. It was a young, restless world still cooling from its fiery birth. As it orbited the Earth's immense gravity exerted a constant pull on it. Now the moon is not a perfect sphere. Its shape is ever so slightly stretched by the Earth's gravity, with subtle bulges both on the side facing us and on the side facing away. These are the tidal bulges, much like the tides our own planet experiences in its oceans. As the early moon spun around, these bulges would be constantly pulled back into alignment by the Earth's gravity. The gravitational pull on the bulge closest to Earth was stronger, and this persistent differential pull created a subtle rotational force, a kind of braking effect. Think of it like a gentle, unseen hand that was ever so slowly, ever so patiently slowing a spinning top. This wasn't a sudden jarring stop. It was a gradual, relentless, and almost imperceptible process. Over hundreds of millions, perhaps even billions of years, this gentle hand applied its pressure. The energy from the moon's rotation didn't just vanish into thin air. It was dissipated slowly and surely primarily through internal friction within the moon's rocky interior. It was the moon's own deep geological heart, resisting the constant tug, generating a minuscule amount of heat, a whisper of warmth that was the byproduct of this immense cosmic negotiation. This process continued unwavering until a perfect state of equilibrium was reached. And what a beautiful, stable state it is. The moon's period of rotation on its axis precisely matched its period of revolution around the Earth. In a grander, more poetic sense, the moon takes the same amount of time to spin around once as it does to complete one slow, majestic orbit around our planet. This is the synchronized dance of two partners who have found their perfect rhythm. One partner, our Earth, leads with a powerful gravitational pull, and the other, the moon, responds by adjusting its steps until they are perfectly in sync. From our perspective here on Earth, it can appear as though the moon isn't rotating at all, that it's just a static orb in the sky, but it is indeed rotating. Its spin is just perfectly beautifully matched with its orbital speed. To help us visualize this, let's imagine a different kind of dance. Picture a person walking around a merry-go-round always facing the central pole. To an observer standing outside the merry-go-round, the person is clearly rotating their body turns to keep facing the center. But to the person on the ride, and relative to the central pole, they are not rotating at all. The moon performs a similar quiet rotation, perfectly matched to its journey. This elegant, tidally locked state, is the most energetically favorable configuration for the system. It minimizes the gravitational stresses, a peaceful resolution to an ancient cosmic argument. This phenomenon, this perpetual facing of one side toward a parent body, is not a unique or strange anomaly in our solar system. In fact, it is quite a common outcome of powerful gravitational interactions over vast timescales, particularly for moons orbiting relatively close to massive planets. For instance, the small moon Charon is tidally locked to Pluto. But in an even more extraordinary twist, Pluto is also tidally locked to Charon. They are two partners in a truly unique waltz, perpetually showing the same face to each other as they circle a common point in space. It is a testament to the powerful shaping hand of gravity, a force that can turn wild, chaotic motion into a quiet, harmonious, and enduring rhythm. It is a force that reminds us of the delicate balance and deep history hidden within the serene face of the night sky. However, the story of the moon's rotation is not quite as simple as a perfect static lock. There is a delightful and subtle exception to this rule, a small grace note in the cosmic melody, a phenomenon known as libration. These librations are small oscillations or wobbles in the moon's apparent position as seen from Earth. They are the little nods and gentle tilts that allow us to peek just a little bit around the moon's edges, revealing a sliver of territory that would otherwise be forever hidden. They remind us that even in a perfect, tidally locked dance, there are still slight movements, small moments of sway and turn. There are several types of these librations, each adding to the intricate viewing geometry that we experience. The first, and perhaps most intuitive, are the optical librations. These are caused by changes in our viewing angle as the moon travels along its path. To understand this, we must remember that the moon's orbit around Earth is not a perfect circle, but an ellipse, a gentle oval. When the moon is at its closest point to Earth in its orbit, it moves a little faster. When it is at its farthest point, it moves a little slower. But here is the key: its spin rate. The rate at which it rotates on its axis remains nearly constant throughout this journey. This subtle difference in speed, a faster orbital pace at times, a slower one at others, allows us to sometimes peer just a little bit around the eastern and western limbs of the moon. It's like watching a runner on an oval track. If they run faster on one side of the track, but keep their head turned at a constant rate, we would be able to see a little bit of their face from the side as they speed up. The moon does this for us ever so slightly. It's a gentle peek around the corner, revealing a little more of the surface. Another type of optical libration is caused by the tilt of the moon's axis relative to its orbital plane. Just as our Earth's tilt causes the seasons, the moon's own subtle tilt allows us to see slightly over its north and south poles at different times of the month. It's as if the moon is a dancer who, while always facing you, sometimes tilts their head slightly up and then slightly down, letting you catch a glimpse of the crown of their head or the tips of their toes. These small rhythmic nods and tilts are a beautiful reminder that the moon is a dynamic spherical world, not a flat static disk. So while a core 50% of the moon's surface is always visible, and another 50% is always hidden, these gentle librations open up a small window. There is a sliver of territory, roughly 9% of the moon's total surface, that sometimes swings into our view and sometimes swings out of view, depending on these subtle wobbles. It's a liminal space, a zone of twilight and transition. This means that over the course of a full lunar cycle, a total of approximately 59% of the moon's surface can be seen from Earth. We do not get to see the entire surface, but we do get to see a little more than half. This leaves us with the vast, truly hidden portion of the far side, approximately 41% of the moon's surface that, no matter how we watch, no matter how patiently we observe, and no matter how powerful our telescopes, remains forever out of our direct line of sight. It is this large, truly hidden portion that constituted the enduring mystery, the blank page, that so captivated our imagination and fueled our curiosity for millennia. It is a part of our closest neighbor that simply refused to show itself shrouded in an enduring mystery that only modern spaceflight could begin to unravel. This perpetual hiding created a vacuum of knowledge that was filled with both scientific conjecture and imaginative speculation. For thousands of years, the terrain, the features, and the very nature of this hidden side remained entirely unknown. Ancient astronomers, keen observers of the night sky, could map the features of the near side with increasing detail, even assigning names to its craters and seas and weaving stories around its shadows. Yet the other half of our lunar companion was a blank canvas, a realm of pure thought and imagination. No telescope, no matter how powerful or refined, could bend light around the moon to reveal its unseen hemisphere. From the earliest rudimentary spyglasses of Galileo Galilei in the 17th century to the massive ground-based observatories of the 20th century, every instrument was fundamentally limited by the moon's tidally locked orientation. We, as a species, could only observe what was presented to us, and the far side steadfastly refused to show itself. This lack of direct observation meant that early lunar maps were by definition incomplete. They represented only the visible surface, leaving the reverse side to the realm of artists' imaginings and educated guesses. Without empirical data, scientists could only hypothesize about its appearance. Some might have assumed it was similar to the near side, while others might have speculated it was vastly different. There was simply no way to confirm or deny these theories from Earth. The advent of photography in the 19th century allowed for more detailed and permanent records of the near side, but it did nothing to pierce the veil of the far side. Even as mapping techniques advanced, creating intricate topographical charts of the visible lunar surface, the far side remained a cartographical void. The true reason for its prolonged mystery was the absence of a crucial technological leap, the ability to leave Earth's gravity and physically go there. Until the mid-20th century, the concept of sending probes beyond Earth's atmosphere was largely confined to the pages of science fiction. The engineering challenges were immense, bordering on the impossible, but the human desire to see the unseen, to know the unknown, was a powerful quiet force, building like a great slow tide, waiting for its moment to break free. It was a moment that would finally arrive with the dawn of the space age, forever changing our relationship with our silent lunar partner. And it is here at the edge of this great mystery that our journey truly begins. We have looked at the moon for so long, and yet we have only seen half of its story. The other half lies waiting in the dark, a canvas of ancient secrets and silent history. What could possibly be out there? How did we finally get to see it? And what did those first glimpses tell us? Let us now drift from the quiet mechanics of orbital physics and into the deep contemplative stillness of human history. For in a way, the story of the moon's far side is not just a tale of gravity and celestial motion, but a story of human imagination and the boundaries of our perception. For thousands of years, as our civilization grew from scattered villages to sprawling empires, the hidden hemisphere of our lunar companion remained a complete mystery, an unspoken secret held close by the cosmos. It was a blank page, a void in our knowledge, and that very emptiness became a canvas for our deepest thoughts and most fantastic imaginings. There was a time when the moon itself was a mystical object, a luminous orb in the night sky that inspired awe, wonder, and countless myths. It was a silver chariot, driven across the heavens, a watchful eye, or a powerful deity influencing tides and harvests. In these ancient thoughts, there was no notion of a physical journey to this celestial body. The moon was a place of spiritual significance, not a destination for flesh and blood. And in that realm of myth, the far side was, if it was considered at all, an even deeper, more profound mystery. Was it the home of the moon's gods, or the resting place of a silver queen? Was it a place of calm, or a region of cosmic storms? We can only imagine the stories whispered around ancient fires, stories that were by their very nature impossible to verify. as humanity's understanding slowly patiently shifted from myth to philosophy, and from philosophy to the nascent stages of science, the nature of this hidden side remained just as elusive. The ancient Greek thinker Anaxagoras in the 5th century BCE boldly suggested that the moon was a rocky body, similar to Earth illuminated by the sun, rather than a divine light source. This was a radical idea for his time, a gentle whisper of empirical truth that challenged prevailing mystical beliefs. It was a small but foundational step toward seeing the moon as a world in its own right. But even with this new way of thinking, the other half of that world remained by definition an unknown. Aristotle, another towering figure in ancient Greek philosophy, built upon these observations, integrating them into his geocentric model of the universe. While his model was ultimately incorrect, his systematic approach to observing and theorizing about the cosmos influenced thinkers for over 1,000 years. Yet the far side of the moon remained a silent, unaddressed enigma within his grand system. The dream of flying, of transcending earthly bounds, also permeated ancient thought, from the myth of Icarus attempting to fly to the sun with wax wings to early allegories about conquering the skies. While these were not direct dreams of space travel, as we understand it, they represented a fundamental human yearning to escape the confines of Earth's surface, a precursor to the grander ambition of reaching other celestial bodies. But for many centuries, the lack of fundamental scientific understanding about physics, gravity, and atmospheric conditions meant that the concept of traveling to the moon remained firmly in the realm of fantasy and allegory. It was a subject for poets and storytellers, not for engineers or scientists. The real shift in our perception of the moon as a physical place began in the 17th century with the invention of the telescope. When Galileo Galilei turned his simple, refined instrument skyward in the early 1600s, he revolutionized our understanding. Through his looking glass, the moon was no longer a perfect smooth sphere, as previously thought, but a rugged world with mountains, valleys, and craters resembling landscapes on Earth. He even estimated the heights of lunar mountains by observing the shadows they cast. This empirical evidence, derived from direct observation, solidified the idea of the moon as a physical body, a world in its own right, rather than a luminous projection or a divine entity. But here is where the story of the far side becomes even more poignant. Even with the invention of this revolutionary tool, the veil remained. Galileo and all those who followed him, from the most enthusiastic hobbyist to the most meticulous professional astronomer, were fundamentally limited by the moon's tidally locked orientation. No matter how powerful their telescopes became, they were in a very real sense simply looking at the same picture, only in a higher resolution. No instrument on Earth, no matter how refined, could bend the laws of physics to see around the corner. The far side steadfastly refused to show itself, and the human eye, no matter its technological augmentation, was bound by the same physical constraints. This lack of direct observation meant that even the most advanced lunar maps of the time were by definition incomplete. They were a testament to the meticulous observation of the near side, filled with the named seas of tranquility, storms, and serenity, but they were half-truths. The reverse side remained a cartographical void, a blank space on the parchment where artists and theorists could only place their educated guesses. Without any empirical data, scientists could only hypothesize. Was it similar to the near side with its mixture of bright highlands and dark Maria? Or was it vastly different, a landscape shaped by some unknown process? There was simply no way to confirm or deny these theories. It was a puzzle with half of its pieces missing, and a profound, quiet sense of frustration must have settled in the minds of those who so passionately studied the night sky. The advent of photography in the 19th century allowed for more detailed and permanent records of the near side, capturing its intricate topography with a fidelity that had been impossible with hand-drawn maps. But even this technological leap did nothing to pierce the veil of the far side. As mapping techniques advanced, creating intricate topographical charts of the visible lunar surface, the far side remained an empty place on the map, a continent of the imagination. The true reason for its prolonged mystery was not a lack of curiosity or intelligence, but the absence of a crucial technological leap, the ability to leave Earth's gravity and physically go there. Until the middle of the 20th century, the concept of sending probes beyond Earth's atmosphere was largely confined to the pages of science fiction. The engineering challenges were immense, bordering on the impossible. The idea of developing rockets powerful enough to escape Earth's gravity, designing guidance systems capable of precise trajectories over vast distances, and creating communication systems that could transmit data back to Earth from interplanetary space, these were not trivial hurdles. They represented the very cutting edge of scientific and engineering endeavor for their time, and the very concept was seen by many as a fantastic, almost foolish dream. This technological chasm meant that for centuries the far side was not just hidden, it was fundamentally unreachable. It was a problem that could not be solved by a more powerful telescope, a new kind of camera, or a more brilliant mathematician. It required an entirely new field of engineering, a new way of thinking, and a monumental collective effort. And even once the idea of space travel began to move from the pages of novels to the blueprints of engineers, the far side presented a unique and immediate problem that was in many ways more challenging than simply getting to the moon itself. This was the problem of communication. Imagine trying to have a conversation with someone on the other side of a very large hill. Your voice simply would not carry. For a spacecraft on the far side of the moon, the problem is precisely the same, only on a cosmic scale. The moon itself is an immense solid barrier, a great stone wall blocking the direct line of sight between the spacecraft and its home planet. There would be no direct path for radio signals to travel back to Earth. Any data it collected, any images it captured, would be trapped on board unless a solution was found. For a mission to the near side, communication was straightforward. The spacecraft always had a clear view of the Earth. But for a mission to the far side, that crucial link was severed the moment the spacecraft rounded the lunar limb. This communication blind spot created a new kind of silence, a period of utter isolation for any mission attempting to explore the hidden hemisphere. It was a problem that necessitated the development of entirely new technologies, such as orbiting satellites, that could act as intermediaries receiving signals from a far-side probe and then retransmitting them back to Earth. Without such relays, long-duration missions to the far side would be impossible to control or to retrieve data from. The simple act of seeing the far side was a technological challenge, but the more profound challenge was the act of listening to what it had to say. The dawn of the space age, sparked by the launch of Sputnik 1 by the Soviet Union in the mid-1950s, fundamentally altered this reality. Suddenly, what was once pure fantasy became a tangible goal. The race to the moon intensified, driven by geopolitical competition and an insatiable scientific curiosity. But even with powerful rockets, the unique problems of the far side, its inherent invisibility, and its profound communication challenge meant that it would not be easily revealed. The secret that had been kept for billions of years would require not just a bold journey, but an act of extraordinary ingenuity to finally be told. And with the first whispers of that new age, the dream of a hidden moon began its long, arduous transformation from a whispered myth to a photograph, however blurry. Let us now turn our minds from the quiet, eternal mystery of the moon's hidden side to the restless, ambitious stirrings of the human spirit and here on Earth. For while the moon's secret was a story billions of years in the making, the journey to finally unveil it was a tale that began not with rockets, but with dreams, with the stories and imaginative leaps that bridged the immense gulf between pure fantasy and the burgeoning fields of physics and engineering. The true reason we eventually saw the unseen was because for centuries, a few remarkable minds dared to imagine the impossible to write it down, and then finally, to do the hard work of making the equations fit the fantasy. The dream of flying to the moon was a potent one long before any science could possibly support it. It was a theme that appeared in ancient allegories and early literature, where the heavens were a canvas for our aspirations. But it was in the 17th century, in the wake of Galileo's revolutionary observations, that this dream began to take a more grounded, albeit still fictional form. Inspired by the new understanding that the moon was a world of mountains and valleys, writers began to pen early works of science fiction that explored the idea of traveling to it. It was a leap of the imagination that followed a leap of observation. Consider, for example, Cyrano de Bergerac, a French playwright and duelist, who in the mid-1600s wrote The Other World, a comical history of the states and empires of the moon. His methods of reaching the moon were wildly fantastical, from using bottles filled with dew that would evaporate and lift him skyward to rockets powered by firecrackers. While scientifically absurd, his work was significant because it was a deliberate attempt to imagine the mechanics of such a journey, to portray a world on the moon with its own inhabitants and society. It was a precursor to a new kind of storytelling, one that grappled with the challenges of space, even if those challenges were entirely speculative. Around the same time, Francis Godwin, an English bishop, published The Man in the Moon, where his protagonist travels to the moon in a device pulled by trained geese. These narratives, though, a world away from any kind of reality, represented a nascent human desire to not just look at the moon, but to consider the practicalities, the what-ifs of a journey there. They were the gentle whispers of a dream that would one day become a reality. This speculative fiction flourished further in the 18th and 19th centuries, increasingly intertwining scientific concepts with imaginative storytelling. But it was in the 19th century that a literary titan, Jules Verne, a French novelist, took the idea of space travel and grounded it in the meticulous, systematic thinking of his era. His 1865 novel, From the Earth to the Moon, is perhaps the most famous and influential work of early space travel fiction. Verne's concept for lunar travel was a giant cannon firing a projectile containing passengers toward the moon. While a cannon launch would be lethally impractical in reality, due to the immense G-forces, Verne meticulously calculated the trajectory, the required muzzle velocity, and even the dimensions of his fictional space gun. He described the challenges of living in a projectile during flight and the experience of weightlessness, demonstrating a remarkable effort to root his fiction in the scientific knowledge of his time. His work captivated public imagination and subtly introduced the principles of ballistics and trajectory to a wide audience. It was a bridge from pure fantasy to something that felt to the average person excitingly plausible. Another prominent 19th century author, H.G. Wells, contributed significantly to the genre with his 1901 novel, The First Men in the Moon. Wells conceived of a more scientifically imaginative method of propulsion, a substance called cavorite, which could nullify gravity. While entirely fictional, this concept allowed Wells to explore the idea of controlled flight to the moon and the challenges of returning. He also created a vivid portrayal of an alien civilization inhabiting the moon, adding a layer of sociological and philosophical inquiry to the space travel narrative. These literary works were crucial in cultivating a widespread public fascination with space travel, transforming it from an obscure scientific concept into an exciting and attainable future endeavor. They were the stories that planted the seed of an idea, a vision of what might be possible in the minds of the people who would one day build the machines to do it. But a dream, no matter how vivid, is not enough to get you to the moon. The true intellectual groundwork for space travel began to be laid by a remarkable group of visionaries in the late 19th and early 20th centuries, often working independently and against considerable skepticism. They were the quiet thinkers, the patient pioneers, who turned the poetic idea of a journey to the stars into the cold, hard reality of mathematics and engineering. One of the most significant theoretical pioneers was Konstantin Tsiolkovsky, a Russian schoolteacher and self-taught scientist. Working in relative isolation in the late 1800s and early 1900s, Tsiolkovsky developed the fundamental principles of rocketry. He famously formulated the rocket equation, a mathematical formula that describes the velocity change a rocket can achieve based on the exhaust velocity of its propellant and the mass ratio of the rocket, the ratio of its initial mass to its final mass after expelling propellant. This equation, deceptively simple on its face, was a revelation. It was the blueprint for getting to space, and it demonstrated that high exhaust velocities and efficient fuel usage were paramount for achieving spaceflight. To understand this with a gentle metaphor, think of it like a balloon that you inflate and then let go. The air rushing out the back pushes the balloon forward. The rocket equation tells us that if you want the balloon to go faster, you need the air to come out more quickly, and you need the balloon to be mostly air in the beginning, with as little material weight as possible. Tsiolkovsky was also a strong proponent of liquid-fueled rockets, recognizing their superior thrust and controllability compared to solid-fueled alternatives. He conceptualized multi-stage rockets, understanding that shedding spent fuel tanks and engines during flight would dramatically increase efficiency and enable higher velocities. He even theorized about the use of liquid oxygen and liquid hydrogen as propellants that are still used in modern spaceflight today due to their exceptional energy density. Beyond the technical specifics, Tsiolkovsky was a deep philosophical thinker who believed that humanity's destiny lay in space. He envisioned space stations, lunar bases, and the colonization of the solar system, articulating a grand vision for human expansion beyond Earth. His work, though largely unknown outside of Russia during his lifetime, provided the theoretical blueprint for subsequent practical developments in rocketry. He was a quiet architect of a future he would never live to see. Across the Atlantic in the United States, Robert Goddard, an American physicist, was independently pursuing his own pioneering work in rocketry. Often ridiculed by the press and misunderstood by the public for his seemingly outlandish ideas, Goddard was a tireless experimenter. While Tsiolkovsky was the theorist, Goddard was the doer. He was the one who put the equations to the test with fire and metal. In 1926, he achieved a monumental feat, the launch of the world's first liquid-fueled rocket. This small rocket named Nell flew only a short distance and for a few seconds, but it was a transformative moment. It proved in tangible physical terms the viability of liquid propellant rocket technology. It was the first wobbly step of the dream-taking flight. Goddard continued to develop and test more powerful rockets throughout his career, often facing funding challenges and working with limited resources. He patented numerous inventions critical to rocket design, including multi-stage rockets, fuel pumps, and guidance systems. His meticulous hands-on approach and persistent experimentation laid the practical foundation for rocketry in the United States. He solved many engineering problems that Tsiolkovsky had only theorized about, bridging the gap between abstract mathematical principles and functional hardware. In Germany, Hermann Oberth, a physicist and engineer, was another key figure in the theoretical development of spaceflight during the early 20th century. His 1923 book, The Rocket into Interplanetary Space, rigorously explored the mathematics and physics of rocket propulsion. Oberth also contributed significantly to the concept of space stations and the use of rockets for scientific research. He influenced a generation of German rocket scientists, including Wernher von Braun, who would later play a crucial role in both military rocketry and the American space program. Together, Tsiolkovsky, Goddard, and Oberth are often referred to as the fathers of rocketry. Their independent yet converging work formed the bedrock of modern astronautics. Their theoretical calculations showed that escape velocity, the minimum speed an object needs to break free from a planet's gravitational pull, was achievable with rockets, moving the idea of space travel from the realm of the impossible to the realm of the challenging, but attainable. But a dark and ultimately accelerating chapter in this story was to come. The grim reality of World War II inadvertently propelled rocket development far beyond what these lone pioneers could have ever achieved on their own. The German V-2 rocket, developed under the leadership of Wernher von Braun, was a military weapon, but it was also the world's first large-scale, liquid-fueled ballistic missile capable of reaching the edge of space. The V-2 demonstrated the immense power and potential of rocket technology in a terrible and destructive way. After the war, both the United States and the Soviet Union acquired German rocket scientists and V-2 technology, which provided a significant leap forward in their respective missile and nascent space programs. This wartime development, while destructive in its original intent, provided invaluable knowledge and hardware that directly contributed to the post-war space race. The intellectual groundwork was now in place, and the hardware had been proven, albeit for a different, darker purpose. The dawn of the Cold War in the mid-20th century then provided a powerful geopolitical impetus for space exploration. The space race between the United States and the Soviet Union became a proxy battle for ideological supremacy, technological superiority, and national prestige. The launch of Sputnik 1 by the Soviet Union in October of 1957, the first artificial satellite to orbit Earth, sent shockwaves through the United States. It demonstrated Soviet technological prowess and ignited a fierce determination in the U.S. to catch up and surpass. This single event, a small beeping satellite in the sky, was the moment the quiet dream of the pioneers became a monumental national endeavor. The technological groundwork was now laid, and the political will was now undeniable. A dream that had been born in myth and nurtured in the minds of a few solitary thinkers was now a national mission, a race to the moon, and a race to finally, for the first time, answer the question of what was on the other side. The quiet intellectual whispers of the rocket pioneers in the early 20th century and the grim accelerations of wartime rocketry all converged in the mid-1950s with the dawn of the Cold War. The race to the moon was not born of pure scientific curiosity alone. It was a feverish geopolitical contest for technological and ideological supremacy. And in that first breathless sprint, one nation moved with astonishing speed and boldness. The Soviet Union, having stunned the world with the launch of Sputnik 1, was not content to simply orbit the Earth. Their ambition was grander, their sights set on the moon itself. They were the first to not only dream of a hidden lunar hemisphere, but to build the machine that would for the very first time turn that dream into a blurry, grainy, but undeniable reality. The mission responsible for this groundbreaking achievement was Luna 3, a robotic probe launched by the Soviet Union in October of 1959. This timing placed it just over 2 years after the momentous launch of Sputnik 1, which had sent shockwaves across the globe. The Luna 3 mission was audacious for its time, a testament to the engineering capabilities of the late 1950s. It was designed not just to orbit Earth, but to journey towards the moon, swing around it in a wide arc, and then, from that distant perspective, transmit images back across the vast distance of space. Its primary objective was singular and revolutionary: to photograph the side of the moon that had never before been seen by human eyes, or indeed by any terrestrial instrument. It was a mission to peel back a veil that had hung for billions of years. The design of the Luna 3 spacecraft was a beautiful blend of primitive technology and ingenious solutions constrained by the tools of its era. It was a cylindrical craft, tapering at one end, equipped with solar panels to generate electrical power and antennas for communication. But the heart of the mission was its imaging system, which seems almost quaint by today's standards. It consisted of a pair of cameras with different focal lengths, allowing for both wider views and slightly more zoomed-in shots. This wasn't a digital camera, of course. It was a camera that used traditional film, much like the kind that people used in their handheld cameras on Earth. What made the system particularly clever, and indeed challenging, was its onboard film processing capability. Once the images were captured, the film would be automatically developed, fixed, and dried within the spacecraft itself, all while traveling through the harsh vacuum of space. It was like a miniature automated darkroom floating in the cosmic abyss. Following the onboard development, the images on the film had to be converted into an electronic signal for transmission back to Earth. This was a far cry from the high-speed digital transfers we take for granted today. Instead, it was achieved by a process similar to early television broadcasting. A tiny light spot would scan the developed film line by line, detecting variations in light and shadow. These variations were then translated into a weak electrical signal, which was then radioed back to receiving stations on Earth. This method was inherently prone to noise and distortion, contributing significantly to the low quality of the resulting images. The communication link across hundreds of thousands of miles was tenuous, a faint whisper in the cosmic roar, and the signal received on Earth was incredibly weak, requiring powerful antennas and sophisticated signal processing to extract any meaningful data. It was like trying to hear a secret from a million miles away with nothing but static in between. The trajectory of Luna 3 was also a masterpiece of early space navigation. Unlike later missions that would aim for a precise lunar orbit or a soft landing, Luna 3 was designed for a circumlunar flyby. It launched from Earth, traveled directly towards the Moon, and then used the Moon's own gravity to alter its course, swinging around the far side before heading back towards Earth. This gravitational slingshot, a clever maneuver that is now a standard tool in interplanetary travel, was a brilliant way to achieve the desired path without requiring excessive amounts of propellant. The timing of the photography was critical. The spacecraft had to be positioned correctly relative to the Moon's rotation and the Sun's illumination to capture the far side in sunlight. It was a precise, high-stakes choreography of motion and timing. On the 7th of October in the year 1959, as Luna 3 arced around the Moon, its cameras snapped pictures of the previously unseen hemisphere. The images once transmitted back to Earth were indeed blurry. They were characterized by low resolution, making it difficult to discern fine details. Streaks and static often marred the frame's artifacts of the primitive transmission technology and the vast distance the signals had to traverse. Yet, despite their imperfections, these images were nothing short of breathtaking. They were the very first empirical evidence of what lay on the other side of our Moon. A mystery that had persisted for all of human history had, in a single moment, been solved, however crudely. The most immediate and striking revelation from these initial blurry photographs was the stark difference between the far side and the familiar near side of the Moon. The near side, as we all know, is easily recognizable by its extensive, dark, relatively smooth plains, known as maria or seas, which are actually vast basins formed by ancient volcanic eruptions that subsequently filled with solidified lava. These maria cover a significant portion of the near side, giving it its distinctive face-like appearance. The Luna 3 images, however, showed a strikingly different landscape for the far side. It was predominantly covered in rugged, heavily cratered terrain, with a notable absence of the large dark maria that characterized the visible lunar landscape. Only a few smaller, irregular dark patches vaguely resembling maria were discernible. This initial revelation was a profound fundamental discovery that shattered centuries of speculation. The far side was not simply a mirror image of the near side. It possessed distinct geological characteristics that hinted at a different evolutionary history. Scientists quickly deduced that the far side had likely experienced a different geological history compared to the near side. The greater abundance of craters suggested an older, less geologically active surface, one that had not been resurfaced by extensive lava flows in the same way the near side had been. The excitement generated by these first distant photographs was immense, confirming the potential for entirely new scientific discoveries. The impact of Luna 3's achievement reverberated far beyond the scientific community. It was a massive propaganda victory for the Soviet Union at the height of the space race, demonstrating their continuing technological lead. For the broader public, it was an awe-inspiring moment, suddenly making the Moon feel less mysterious and more like a real, albeit alien world. The photographs sparked immense public interest and fueled further scientific curiosity about the Moon. They confirmed that humanity had the capability to venture beyond Earth's immediate vicinity and to reveal the secrets of other celestial bodies. The mission provided crucial data that influenced future mission planning for both Soviet and American space programs. For the Americans, who were then in the early stages of establishing NASA and planning their own lunar missions, Luna 3's findings provided invaluable intelligence about the lunar environment. It underscored the need for detailed mapping and reconnaissance of the Moon's entire surface, not just the familiar near side. The experience gained in orbital maneuvers, remote imaging, and long-distance communication from Luna 3, though Soviet offered lessons that could be studied and adapted by other spacefaring nations. The blurry images were not just photographs. They were a window into a previously unimaginable world, opening new avenues for scientific inquiry and setting the stage for the more detailed explorations that would follow. They marked a profound shift from speculation to empirical observation in our understanding of our nearest celestial neighbor. The hidden moon was hidden no more, at least in a general sense, and the blurry outlines of its true face began to emerge from the cosmic dark. The story of what followed would be a tale of American ambition, a systematic and methodical effort to not just see this new world, but to truly understand it and eventually to walk upon it. The blurry revolutionary images returned by the Soviet Union's Luna 3 probe were more than just photographs. They were a profound challenge. They proved that the moon's hidden side was real. It was different, and it was attainable. For the United States, this achievement followed a series of Soviet firsts that had already sent shockwaves across the nation, beginning with the launch of Sputnik 1. The middle of the 20th century was a period of intense global rivalry characterized by the Cold War, and this competition extended beyond terrestrial boundaries, reaching into the vast expanse of outer space. America's response to this series of stunning technological triumphs was not a single dramatic event, but a methodical, determined, and patient process of self-reinvention. It was a national awakening that led to the formation of a single unified civilian agency dedicated to a dream that had until then felt like a fantasy. The catalyst for America's full-fledged commitment to space exploration came on a crisp October day in 1957. On that day, the Soviet Union successfully launched Sputnik 1, the Earth's first artificial satellite, into orbit. The small beeping satellite circling our planet every 96 minutes was not just a technological achievement. It was a powerful symbol of Soviet scientific and military prowess. For the American public, it was a sudden, jarring wake-up call. The event, widely dubbed the Sputnik Crisis, ignited a profound sense of alarm and urgency within the American government and its populace. It suggested that the United States was falling behind, that its technological leadership was in question, and that the heavens themselves might soon become a new theater of a Cold War that had until then been fought in the shadows. Prior to Sputnik, space-related research in the United States was fragmented and disparate. Various military branches, including the Army, Navy, and Air Force, were independently pursuing rocket development, primarily for ballistic missiles. Civilian scientific efforts were also underway, often under the purview of organizations like the National Advisory Committee for Aeronautics, NACA, which had been established in the early 1900s to conduct aeronautical research. However, there was no single unified civilian agency dedicated to exploring space for peaceful scientific purposes. The fragmented nature of American efforts meant that resources were sometimes duplicated and coordination was often lacking, leaving the nation seemingly behind in the initial stages of the space race. It was a collection of brilliant minds working in their own quiet corners without a shared powerful North Star to guide them. The Sputnik launch made it abundantly clear that a more cohesive and centralized approach was desperately needed if the United States was to compete effectively in this new frontier. Recognizing the strategic and scientific imperative, President Dwight D. Eisenhower took decisive action. He understood that the American response needed to be robust, comprehensive, and clearly focused on peaceful exploration rather than purely military applications. On the 29th day of July in the year 1958, President Eisenhower signed the National Aeronautics and Space Act into law. This landmark legislation officially created the National Aeronautics and Space Administration, NASA. The new agency was designed to consolidate and lead all civilian space activities in the United States. Its mandate was clear: to organize and conduct aeronautical and space activities for peaceful purposes benefiting all of humankind. This was a crucial distinction from the Soviet Union's more militarized space program. NASA was effectively built upon the foundation of NACA, which ceased to exist as a separate entity. NACA's highly skilled engineers and scientists, along with its extensive research facilities, were absorbed into the new agency, providing an immediate and substantial technical workforce. Additionally, various other military and civilian research groups and projects were transferred to NASA, including the Jet Propulsion Laboratory JPL and elements of the Army Ballistic Missile Agency. This consolidation brought together disparate talents and resources under one roof, providing the necessary infrastructure and expertise to embark on ambitious space endeavors. It was a moment of gathering, of collecting all the scattered pieces of a dream and placing them in a single, well-lit room. NASA's initial structure was designed to be agile and responsive, capable of managing large complex projects that would push the boundaries of technology and human endurance. Its goals were not modest. They quickly expanded from simply launching satellites to putting humans into orbit and eventually to sending them to the moon. NASA's early goals for lunar exploration were ambitious and systematically planned, evolving from simpler human spaceflight missions to the ultimate lunar landing. Project Mercury was the first and most crucial step in this grand human spaceflight endeavor. Its primary objective was to determine if humans could survive and function in the harsh environment of space. Launched in the early 1960s, Mercury missions involved single astronauts in small capsules that orbited Earth for short durations. These flights were crucial for understanding the effects of weightlessness on the human body, testing life support systems, and developing the critical procedures for launch, orbital flight, and safe re-entry. The success of Project Mercury, including Alan Shepard's suborbital flight and John Glenn's orbital flight, proved that humans could indeed operate effectively in space, laying the psychological and practical groundwork for more complex missions. It was the first quiet step of a long journey, proving that the human body could endure what the dream required. Building upon the experience gained from Mercury, NASA launched Project Gemini. This program, conducted in the mid-1960s, involved two-person spacecraft and was designed to develop the advanced capabilities necessary for a moon landing. Gemini missions focused on mastering critical techniques such as orbital rendezvous and docking, which would be essential for connecting the lunar module to the command module in lunar orbit during an Apollo mission. Astronauts also performed spacewalks, extravehicular activities, testing their ability to work outside the spacecraft in the vacuum of space. Gemini missions lasted for longer durations than Mercury, providing more data on long-term human endurance in space. These 12 Gemini flights were vital proving grounds, systematically perfecting the maneuvers and procedures that would be absolutely necessary for the complex journey to the moon. It was a methodical dress rehearsal where every move was practiced, every detail perfected in preparation for the performance of a lifetime. The ultimate objective of these preparatory programs was Project Apollo, a monumental undertaking aimed at landing humans on the moon and returning them safely to Earth. President John F. Kennedy's bold challenge in 1961 to land a man on the moon before the end of the decade galvanized the nation and set a clear, ambitious target for NASA. However, before humans could land, a vast amount of basic information about the lunar surface was required. The far side was still only a blurry, incomplete picture from Luna 3, and even the near side, the intended landing zone, was full of unknowns. Scientists and engineers needed to know if the surface was firm enough to support a lander, what the soil was made of, and what the topography of potential landing sites looked like in detail. The risks of sending humans to an unknown destination were immense, and the stakes were too high to proceed without careful reconnaissance. This is where NASA's initial uncrewed missions, which we will explore in our next chapter, played an absolutely critical role. They were the robotic scouts sent ahead to gather vital intelligence about the moon's environment and geology to de-risk the future human missions. The dream of the pioneers was now a collective national goal, backed by massive funding and political will. But it was a dream that had to be built, one careful, methodical, and technological step at a time. And the first steps of that final grand act were taken not by human feet, but by the cameras and instruments of patient robotic explorers, venturing into a world that was still, for the most part, a magnificent and terrifying unknown. The grand ambition of Project Apollo, with its clear, audacious goal to land a human on the moon, was a magnificent dream. But before that dream could become a reality, there was a vast and terrifying chasm of unknowns that had to be crossed. While the Soviet Union's Luna 3 had given us a blurry first photograph of the far side, the near side, the very ground on which astronauts hoped to land, was still shrouded in immense uncertainty. What was its surface truly like? Was it firm and solid, or was it, as some scientists feared, covered in a deep layer of soft, treacherous dust into which a lander might sink without a trace? The stakes were immeasurably high, and the journey to a human landing could not proceed without first sending a different kind of pioneer. These were the robotic scouts of NASA, the unmanned missions that would take on the riskiest first steps, answering the fundamental questions that were too dangerous to ask a human. NASA's first series of uncrewed missions to obtain close-up images of the moon's surface was the Ranger program. Launched in the early to mid-1960s, these missions had a straightforward and almost brutally elegant objective to fly directly towards the moon, transmit a series of high-resolution television images back to Earth, and then intentionally crash onto the lunar surface. The goal was not a gentle landing, but a final dramatic plunge into the unknown to gather the most detailed data possible in those last precious moments. The early Ranger missions faced numerous challenges and experienced several failures, which were a painful but necessary part of the learning curve in the nascent days of deep space exploration. Technical glitches, ranging from power system failures to instrument malfunctions, plagued the initial attempts. For every successful launch, there was a quiet, heartbreaking moment where the signal was lost and the mission was over. But each failure provided valuable lessons, allowing engineers to refine designs and procedures, strengthening the resolve to press on. And the perseverance finally paid off with Ranger 7. Launched in July of 1964, Ranger 7 was a resounding success. As it plummeted towards the moon, it transmitted over 4,300 close-up images, revealing details far smaller than what could be seen with any Earth-based telescope. These images showed craters as small as a foot across, providing unprecedented detail of the lunar terrain. Ranger 7's success was followed by Ranger 8 in February of 1965 and Ranger 9 in March of 1965. Both of these missions also successfully delivered thousands of high-resolution images, painting a detailed picture of the moon's surface in the final seconds before impact. These Ranger images were instrumental in settling a key debate among lunar scientists at the time. The question of the lunar dust, the possibility of a soft, deep layer, had been a source of immense concern. The Ranger images clearly showed a relatively solid rocky surface, densely covered with craters, but firm enough to support a lander. This information was absolutely vital for the design of the Apollo lunar module's landing gear and for selecting safe landing sites. The clarity of these images also helped scientists understand the lunar regolith, the layer of loose fragmented material covering the moon's surface, and the effects of micrometeorite impacts. The Ranger program, through its fiery one-way journey, had bravely plunged into the unknown and returned a single profound truth. The ground was solid. The first great fear had been put to rest. Following the success of the Ranger impact probes, NASA embarked on the Surveyor program, which represented a monumental leap in lunar exploration capability. The objective of the Surveyor missions was to achieve a soft landing on the moon and to analyze the lunar surface directly. This was a far more complex undertaking than a simple impact. Each Surveyor spacecraft was equipped with a retro-rocket system that would fire to slow its descent, allowing for a gentle touchdown on the lunar surface. The Surveyor design was also much more sophisticated, featuring multiple television cameras to provide panoramic and close-up views of the landing site, as well as instruments to analyze the soil. It was no longer enough to simply see the surface from a distance. Now it was time to touch it, to feel it, and to understand its composition. Surveyor 1 achieved the first successful American soft landing on the Moon in June of 1966. This was a tremendous triumph for NASA, proving the agency's capability to safely land a spacecraft on another celestial body. Surveyor 1 transmitted over 11,000 images of its landing site, showing the landscape in incredible detail. Subsequent Surveyor missions, a total of 7 spacecraft, were launched, with 5 successful landings provided even more critical data. For example, Surveyor 5 carried an alpha scattering instrument, which analyzed the chemical composition of the lunar soil, confirming that it was basaltic, similar to volcanic rocks on Earth. Other surveyors were equipped with scoops that could dig trenches in the lunar regolith, providing direct information on its bearing strength and consistency. This confirmed that the lunar surface was firm enough to support the weight of the Apollo lunar module, and that astronauts could walk on it without sinking. The detailed images from Surveyor missions also helped engineers understand the nature of the rocks, boulders, and terrain that future astronauts would encounter, allowing for crucial refinements in mission planning and astronaut training. The Surveyor program essentially served as the ultimate test and validation for the Apollo landing concept, a gentle handshake with a world that was soon to receive human visitors. But there was one more vital piece of the puzzle that was needed before the human missions could begin in earnest. The Moon in its entirety had to be mapped. While Ranger and Surveyor focused on specific landing areas on the near side, a comprehensive high-resolution atlas of the entire lunar surface was required. This was the role of the Lunar Orbiter program, a series of 5 robotic orbiters launched in the mid-1960s. These spacecraft were the cartographers of the Moon, designed to systematically map its entire surface, including both the near and far sides at high resolution. Their primary goal was to scout and photograph potential landing sites for the Apollo missions, ensuring that the chosen locations were flat-free of large boulders and safe for a human landing. The Lunar Orbiter missions produced a comprehensive photographic atlas of the Moon, revealing details of craters and mountains across the entire globe. While previous missions had given us glimpses and close-ups, these orbiters gave us the whole picture, filling in the gaps of the blurry Luna 3 images and providing a detailed global context for all the other data. This data, combined with that from Ranger and Surveyor, provided an unparalleled understanding of the lunar environment, which was absolutely indispensable for the ambitious Apollo program. These missions, with their quiet, methodical work, laid the scientific and technical groundwork for everything that was to follow. They were the silent pioneers who took on the riskiest first steps, gathering the data, answering the questions, and paving the way for the human footsteps that would soon follow. The journey to unveil the hidden Moon and to land upon its surface was a meticulous step-by-step process. It began with the theoretical musings of pioneers, was accelerated by geopolitical competition, and was ultimately made possible by the patient, unblinking eyes of robotic probes. The Ranger missions plunged into the unknown to prove the ground was firm. The Surveyor missions gently touched down to confirm its strength and composition, and the Lunar Orbiters meticulously mapped the entire world, including the hidden far side, to ensure that the human explorers who would soon follow would know what they were getting into. With all this data now in hand, the stage was finally set for the ultimate act of human courage and ambition, the journey of the Apollo astronauts, who would not only see the hidden Moon, but would be the first to truly describe it from a new, breathtaking perspective. The methodical, unblinking eyes of the robotic scouts, Ranger, Surveyor, and Lunar Orbiter had done their work. They had plunged, they had touched, and they had mapped meticulously, gathering the data that was absolutely necessary to de-risk the greatest journey humanity had ever conceived. The engineers now had their answers. The lunar surface was firm, its soil was understandable, and potential landing sites were charted. The stage was set. But before the final act of landing humans on the moon could begin, one more daring mission was needed. It would be a journey not to land, but to see. It would be the first time human eyes would behold the far side, and the first time human voices would describe it. The pioneering mission that first carried human beings around the moon was Apollo 8. Launched in December of 1968, Apollo 8 was a daring and accelerated mission. A bold strategic shift, born of both a desire to beat the Soviet Union to a major lunar milestone and a confidence in the capabilities of the Apollo command and service modules. The crew of Frank Borman, James Lovell, and William Anders were originally intended for an Earth orbital test flight. However, in a stunning decision, NASA decided to send them directly to the moon. Their mission was simple in its elegance, but profound in its implication to orbit the moon 10 times before returning to Earth. This decision meant that for the first time, human beings would not only journey to another celestial body, but they would pass behind it where no human had ever seen before. The experience was one of immense emotional and psychological weight. As their spacecraft approached the moon, it was a moment of profound anticipation. The familiar, unchanging face that had been a silent companion in the night sky for millennia began to swell in their windows, growing larger and larger until it filled their entire view. And then, as the spacecraft, moving with an impossible speed, arced around the lunar limb, the Earth, their home, their anchor, the blue marble of life began to drop out of view. The direct line of sight with mission control in Houston was severed. This moment, more than any other, marked their transition from being Earthbound observers to truly being interplanetary voyagers. And with the Earth gone, the unknown hemisphere emerged into their sight. The astronauts were the very first humans to see the far side directly, and their live television broadcast back to Earth allowed millions to share in their awe, even if the images were grainy and the descriptions were limited by the transmission technology of the time. What they saw was a landscape that was starkly, profoundly different from the familiar near side. They immediately noticed the absence of the vast, dark volcanic plains or maria that characterized the side of the moon facing Earth. Instead, the far side appeared as an endless expanse of rugged, heavily cratered terrain. Astronaut William Anders famously described it as an immense, forbidding, lonely expanse. This simple, powerful description summed up the feeling of desolation and ancient history that radiated from the landscape. It was a surface churned and pockmarked by billions of years of relentless cosmic impacts. This direct human observation corroborated the earlier blurry images captured by the Soviet Union's Luna 3 robotic probe. But the human eye and the human mind could perceive depth and nuance in a way that early automated cameras could not. The astronauts could see craters superimposed upon craters, a testament to an ancient and relentless bombardment. They could feel the sheer scale and overwhelming desolation of a landscape that had been untouched by the volcanic resurfacing, that had smoothed out much of the near side. It was a raw, unvarnished look at the moon's deep past. The experience of passing over the far side also brought with it a profound period of communication blackout. As the Apollo spacecraft moved behind the moon, the direct line of sight with Earth was severed. For approximately 15 to 20 minutes during each orbit, the crew of Apollo 8 and all subsequent Apollo missions were completely cut off from mission control. This enforced silence was a stark reminder of their immense distance from home and the absolute isolation of their journey. Frank Borman, the commander of Apollo 8, described the feeling as being truly alone in the universe during these blackouts. It was a period of silence and self-reliance, a testament to the fragile yet powerful link that connected them to their homeworld. All communications, telemetry, and navigation updates ceased until the spacecraft re-emerged from behind the lunar disk. The precision of the orbital mechanics meant that mission control could predict the exact moment of blackout and signal reacquisition. But for the crew, it was a powerful, quiet experience of detachment and profound solitude. The Apollo 8 mission was not just a technical triumph. It was a psychological and spiritual one. The crew's broadcast on Christmas Eve of 1968, where they read the first 10 verses of Genesis, and the now iconic photograph of Earthrise, the first image of Earth seen from a distance, had a profound impact on humanity. It was a moment that transcended the geopolitical rivalry of the Cold War and connected billions of people to a single quiet journey. The image of our beautiful, fragile blue marble rising above the gray desolation of the moon was a powerful reminder of our place in the cosmos, a moment of universal reflection that was made possible by the courage of 3 men who dared to go to a world that was still, for the most part, a magnificent unknown. Apollo 8 was followed by Apollo 10 in May of 1969. This mission was a dress rehearsal for the lunar landing, carrying a full Apollo stack, including a lunar module that separated and descended to within 50,000 feet of the lunar surface before rejoining the command module. The crew Thomas Stafford John Young and Eugene Cernan also orbited the moon extensively, providing further human observations of the far side. Their detailed reconnaissance, while primarily focused on mapping potential landing sites on the near side, inherently involved multiple passes over the far side. Their reports echoed the earlier descriptions, a uniform, heavily cratered ancient surface. They often described the vastness of the craters, some appearing to be hundreds of miles across, and the stark contrast between the bright sunlit crater rims and the deep, dark shadows within the craters. The lighting conditions varied, with each orbit offering different perspectives on the intricate topography of the far side, all of which added invaluable detail to the picture that had been painted by the robotic probes. And then, of course, came the historic mission of Apollo 11 in July of 1969, which first landed humans on the moon. While Neil Armstrong and Buzz Aldrin were on the surface, Michael Collins remained in orbit in the command module Columbia. For nearly 28 hours, Collins orbited the moon alone, completing 30 orbits. During each of these orbits, he passed over the far side. His solo journey offered a unique perspective on the isolation and scale of the lunar environment. Collins described the far side as being uniformly pockmarked and conveying a sense of profound loneliness. He noted the constant communication blackout, emphasizing the absolute isolation during those periods. His observations confirmed the uniformity and ancient nature of the far side, reinforcing the robotic findings and adding the invaluable human touch to the scientific record. Collins' detailed recollections of seeing the familiar Earth disappear and the unknown lunar terrain emerge were poignant and reflective, underscoring the deep psychological impact of such a journey. The first direct human observations of the far side were not just about science. They were about poetry, about philosophy, about the very human need to explore and to witness. The blurry images from Luna 3 had given us the first photograph of the far side. The maps from the lunar orbiter had given us a blueprint. But the astronauts of Apollo 8, 10, and 11 gave us the first human testimony. They gave us the first human words to describe a landscape that had been a silent mystery for all of our history. Their courage, their perspective, and their profound sense of wonder, all transmitted from a small metal capsule orbiting a world of silent gray, forever changed our relationship with our lunar companion. The far side was no longer just a blank page on a map. It was a place that had been seen, a place that had been experienced, a place that had been touched by the human spirit. The groundbreaking journey of Apollo 8 and the historic landing of Apollo 11 had turned a centuries-old mystery into a breathtaking, living reality. The far side of the moon was no longer a blank page, but a landscape that had been seen by human eyes. Yet these initial glimpses were just the beginning. The subsequent Apollo missions, while focused on landing in specific scientific regions on the near side, continued to provide extensive human observations of the hidden hemisphere. These journeys offered a more sustained and detailed look at the far side, building upon the initial awe and adding a layer of meticulous scientific scrutiny. This era of exploration was defined by a unique and profound form of solitude, the experience of the command module pilot, the astronaut who remained alone in lunar orbit, a lone sentinel circling a world of silent ancient gray. The astronauts of Apollo 12, 14, 15, 16, and 17 all had the opportunity to view the far side of the moon multiple times during their missions. Their direct visual impressions and recorded data became a crucial complement to the robotic mapping data. While instruments could measure topography and composition with precision, the astronauts provided the qualitative feel, the human impression of what it was like to gaze upon this ancient, forbidding landscape. Their descriptions consistently reinforced the scientific understanding that the far side was fundamentally different from the near side. They noted the ruggedness, the ancient appearance, and the near-total lack of the large dark Maria that defined the visible side. The sun angle played a critical role in their observations. When the sun was low on the horizon, the shadows cast by craters and mountains were long and dramatic, highlighting the intricate topography with a stark three-dimensional clarity. When the sun was high, the surface appeared flatter, but the subtle differences in the reflectivity of the lunar regolith, the layer of loose fragmented material covering the surface, became more apparent. The astronauts were trained to look for specific geological features, and their direct reports, often given live or recorded for later debriefings, provided valuable human validation of the robotic mapping data. For example, observations on the relative density of craters or the presence or absence of certain types of terrain contributed to the overall geological picture. The human eye and brain, capable of synthesizing complex visual information in real time, provided a level of qualitative assessment that even advanced photographic equipment struggled to replicate in the early space age. But perhaps the most unique and introspective observations came from the command module pilots, the astronauts who remained in lunar orbit while their two crewmates descended to the surface. Michael Collins on Apollo 11 was the first, but he was followed by a line of equally brave and solitary explorers: Richard Gordon on Apollo 12, Al Worden on Apollo 15, Ken Mattingly on Apollo 16, and Ron Evans on Apollo 17. They each spent a considerable amount of time alone circling the moon multiple times, often for days on end, observing the far side repeatedly. Their solitude enhanced the experience, making their observations even more profound and reflective. For significant periods, they were the only humans to witness the full sweep of the far side directly. Their detailed descriptions, often published in their post-mission books and interviews, provided rich personal insights into this alien landscape. They spoke of the eerie silence, the absence of any discernible features that suggested life or recent geological activity, and the overwhelming sense of geological time encapsulated in the ancient battered surface. The communication blackout periods during far-side passes were a recurring feature of all Apollo lunar missions. This enforced isolation required precise planning and adherence to strict protocols. Before entering the blackout zone, mission control would transmit final instructions and updates to the crew. The astronauts would then monitor their spacecraft systems independently, relying on onboard computers and their rigorous training. This period was often used for quiet reflection or for specific tasks that did not require real-time communication. The reacquisition of signal after emerging from behind the moon was always a moment of relief and a confirmation that the mission was proceeding as planned. This enforced isolation during each far-side pass became a defining characteristic of lunar orbital flight, reminding the crews of the vast distances involved and the delicate balance of technology that kept them connected to Earth. The experience of the command module pilot, in particular, was a powerful meditation on our place in the cosmos. Al Worden, while on Apollo 15, described the solitude and the beauty of seeing the Earth rise over the lunar horizon, only to have it disappear moments later as he passed over the far side. He was, for that time, the loneliest human in existence, the only one not contained within the safe bubble of Earth's gravity. His observations and those of his fellow command module pilots were not just scientific. They were deeply personal and philosophical. They provided a human counterpoint to the objective data, a sense of lived experience that no camera or sensor could ever capture. The Apollo mission's observations of the far side were not limited to just what the eye could see. The later missions were equipped with a scientific instrument module SIM bay in the service module, which contained a suite of advanced instruments. These included mapping cameras, laser altimeters, and spectrometers that collected systematic data as they flew over the far side. The astronauts' role was to operate these instruments, ensuring they were functioning correctly and collecting the most valuable data. This combination of human presence and advanced instrumentation provided an unparalleled level of detail about the far side's topography, mineral composition, and gravitational field. The human presence in orbit allowed for a level of flexibility and responsiveness that was impossible for the pre-programmed robotic probes. The astronauts could in a sense act as brilliant scientists and technicians, making real-time decisions and observations that enhanced the quality of the data immeasurably. The cumulative human observations from all the Apollo missions greatly enhanced humanity's understanding of the far side. They provided a visual and experiential context to the robotic mapping data, while instruments could measure topography and composition with precision. The astronauts provided the qualitative feel, the human impression of what it was like to gaze upon this ancient, forbidding landscape. Their accounts consistently reinforced the scientific understanding that the far side was fundamentally different from the near side in its geological history. Appearing more ancient, more heavily cratered, and lacking the extensive volcanic resurfacing seen on the Earth-facing side. These human observations confirmed the moon's asymmetry and contributed to the scientific theories explaining this dichotomy, such as differences in crustal thickness and the impact history. The far side, once entirely unknown, slowly yielded its visual secrets to the persistent gaze of human explorers in lunar orbit, adding an invaluable dimension to our knowledge of Earth's closest celestial companion. The legacy of their direct observations continues to inform our understanding of this once mysterious lunar hemisphere. But there is one more deeply dramatic encounter with the far side that must be told. It was not planned, and it was not for science, but for survival. It was the mission of Apollo 13. After a catastrophic in-flight explosion in the service module crippled their spacecraft, the crew had to use the moon's gravity to swing around and return to Earth on a free return trajectory. This path meant passing behind the moon over the far side. For the distressed crew, James Lovell, Jack Swigert, and Fred Hayes, this was a moment of immense tension. During the crucial far side pass, they were entirely cut off from mission control, unable to receive critical updates or send emergency telemetry. This blackout period, normally a routine occurrence, became a period of heightened anxiety as they silently rounded the moon, uncertain if their crippled spacecraft would survive the journey back. Their experience, though not focused on scientific observation of the far side, dramatically underscored the isolating nature of this hidden hemisphere and the critical importance of reliable communication. The far side in that moment was not a place of scientific wonder, but a vast, silent obstacle that they had to navigate in order to get home. It was a powerful and terrifying final testament to the isolation and immense distances involved in our lunar journeys. Let us now, with the gentle rhythm of our journey, turn our minds to a single colossal feature on that silent ancient canvas of the far side. It is a feature so immense, so profound in its scale and significance, that it is not merely a part of the moon's story, but a window into the very beginning of our solar system itself. The moon's surface, as we know, is scarred by countless impact craters, a testament to its long and tumultuous history. These craters range in size from tiny pockmarks to enormous basins, hundreds of miles across. But among these monumental features, one stands out as truly exceptional in its sheer size and the ancient secrets it holds. It is the South Pole-Aitken Basin, or SPA. This colossal impact structure, located on the Moon's far side, is not only the largest and deepest confirmed impact basin on the Moon, but it is also one of the largest and oldest known impact features in the entire solar system. Its immense size and unique location have made it a prime target for scientific investigation by NASA and other space agencies, as it holds invaluable clues about the Moon's formation, its internal structure, and the history of early solar system bombardment. It is, in a way, a cosmic bullseye that has preserved a crucial piece of our universe's origin story. The South Pole-Aitken Basin was not discovered in a single dramatic moment. Its presence was gradually revealed piece by piece through the successive robotic missions that we have already quietly explored. The first hints of its existence came from the blurry images transmitted by the Soviet Union's Luna 3 probe in October of 1959. While these early images were of low resolution, they showed a heavily cratered terrain distinct from the near side, and within that chaos, scientists began to suspect the presence of a vast, subtle depression. As NASA launched its own series of lunar orbiters in the mid-1960s, particularly the Lunar Orbiter program, more detailed photographic coverage of the far side became available. These high-resolution images allowed scientists to begin mapping and identifying the immense, subtle depression that characterized the basin. Later images from Apollo mapping cameras during the human missions provided even better views, further confirming the basin's colossal scale. However, due to its sheer size and the low angle of the Sun at the lunar poles, its full extent and depth were not immediately obvious from photographic data alone. The basin is appropriately named for its location. It encircles the Moon's south pole and extends northward towards the relatively prominent Aitken crater, which serves as a visible landmark near its northern edge. Its shape is roughly circular or somewhat elliptical, reflecting the angle of the impactor that created it. The sheer dimensions of the South Pole-Aitken Basin are staggering and almost impossible to comprehend. It spans approximately 2,500 kilometers, or about 1,550 miles in diameter. To put this in perspective, that is roughly the distance from New York City to Dallas. Its depth is also remarkable, reaching approximately 8 to 13 kilometers, or 5 to 8 miles from its highest rim to its deepest floor. This makes it significantly deeper than the Grand Canyon on Earth and represents a massive, almost incomprehensible excavation of the lunar crust. The age of the South Pole-Aitken Basin is another critical aspect of its scientific importance. Scientists estimate that this immense impact occurred very early in the Moon's history, likely between 4.3 and 4.2 billion years ago. This places its formation within the period known as the Late Heavy Bombardment, a hypothesized era in the early solar system when a disproportionately large number of asteroids and comets collided with the inner planets and their moons. As one of the oldest and largest features on the Moon, SPA serves as a fundamental geological marker, a chronological anchor for understanding lunar history and the wider bombardment history of the solar system. By studying SPA, scientists can gain insights into the chaotic conditions and cataclysmic events that shaped the planets and moons during their infancy. It is a time capsule preserving a record of a violent distant past that has been erased on more geologically active worlds like Earth. NASA's sustained exploration efforts have been paramount in unraveling the secrets of the South Pole-Aitken Basin. Early missions provided photographic evidence, but more sophisticated instruments were needed for detailed characterization. In the early 1990s, the Galileo spacecraft on its way to Jupiter conducted a flyby of the Moon and provided multispectral imaging data, offering new insights into the basin's composition. Shortly thereafter, the Clementine mission launched in 1994, provided a wealth of data, including high-resolution photographic and topographic maps of the lunar surface, and also collected multispectral information that helped define the basin's unique mineralogy. A pivotal mission for understanding SPA was NASA's Lunar Prospector, launched in 1998. Lunar Prospector carried a gamma-ray spectrometer that was crucial for mapping the elemental composition of the lunar surface. For the South Pole-Aitken Basin, this instrument revealed anomalous concentrations of certain elements, particularly iron and titanium, on the basin floor. These higher concentrations were interpreted as evidence of deeper crust or even mantle material, having been excavated by the immense impact and brought closer to the surface. Lunar Prospector also provided critical gravitational field data confirming that the basin had a distinct gravity signature, further reinforcing its massive scale and unique subsurface structure. However, the most comprehensive data on the South Pole-Aitken Basin has come from NASA's Lunar Reconnaissance Orbiter (LRO), launched in 2009 and still operating. LRO has transformed our understanding of the Moon, including SPA, with its suite of advanced instruments. Its Lunar Orbiter Laser Altimeter (LOLA) mapped the basin's topography with unprecedented precision. By bouncing laser pulses off the lunar surface and measuring the time it took for the light to return, LOLA created a highly accurate three-dimensional model of SPA, precisely defining its depth rim structure and the subtle contours of its floor. This allowed scientists to calculate the exact volume of material excavated by the impact, providing crucial data for models of basin formation. LRO's Diviner Lunar Radiometer Experiment. Another key instrument measured temperatures across the lunar surface, providing insights into thermal properties and helping to identify the distribution of various minerals based on how they radiate heat. Combined with data from spectrometers on other missions, compositional maps of SPA became increasingly refined. These maps consistently show that the floor of SPA contains material that is rich in iron and magnesium elements typically found in the Moon's mantle, the layer beneath the crust. This finding strongly supports the hypothesis that the SPA impact was so powerful and deep that it effectively punched through the lunar crust, excavating and exposing material from the Moon's deeper interior. This is of immense scientific interest because it offers a rare opportunity to study the Moon's mantle without having to drill kilometers into its surface. The mantra, "a deep and mysterious layer," remains largely unknown to us, and this single cataclysmic event may have provided us with a natural laboratory to study it. The scientific theories surrounding the formation of the South Pole-Aitken Basin are fascinating and speak to the violence of the early solar system. The prevailing theory suggests that the basin was formed by the impact of an enormous asteroid or comet, possibly hundreds of kilometers in diameter, traveling at incredibly high velocities. Such an impact would have unleashed an unimaginable amount of energy, far exceeding any event witnessed on Earth in recorded history. The sheer force of this collision would have instantaneously vaporized vast quantities of rock, melted more, and ejected colossal amounts of material across the lunar surface and into space. The resulting crater would have been so large that its rim would have immediately begun to collapse inwards, creating the complex multi-ring structure characteristic of such immense basins. Though much of this structure has since been eroded by subsequent impacts, one of the key implications of the SPA impact is the resulting thinning of the lunar crust beneath the basin floor. Models suggest that the impact effectively removed significant portions of the original crust, leaving a thinner, warmer crust layer at the bottom of the basin. Paradoxically, despite this crustal thinning, the South Pole-Aitken Basin does not contain the extensive mare basalts or volcanic plains that are prevalent on the Moon's near side. While some smaller, irregular mare patches exist within SPA, they are not as widespread or voluminous as those found in basins like Mare Imbrium or Mare Serenitatis. This observation has led to complex scientific debate. One theory suggests that while the crust was thinned, the timing of the impact relative to the Moon's internal thermal evolution meant that widespread volcanism did not occur in SPA. Another possibility is that the deep excavation exposed mantle material that was not conducive to forming extensive lava flows, or that the material erupted was too viscous to spread widely. The mantle excavation hypothesis is a cornerstone of SPA's scientific significance. If the impact did indeed bring mantle material to the surface, it provides a unique natural laboratory for studying the Moon's deep interior. Scientists are keenly interested in confirming the presence of pristine mantle rocks, as this would provide direct insights into the Moon's composition beyond its crust. Minerals like olivine and pyroxene, which are common in Earth's mantle, would be strong indicators of exposed lunar mantle material. Remote sensing data from LRO and other orbiters has strongly suggested the presence of these materials, but direct sample analysis would be the definitive proof. Understanding the Moon's mantle is crucial for understanding its overall thermal evolution, its magnetic history, and its differentiation into distinct layers. Furthermore, the SPA impact is thought to have played a significant role in the overall asymmetry observed between the Moon's near and far sides. The immense amount of energy released and the massive redistribution of mass caused by the impact would have profoundly influenced the Moon's gravitational field and its internal stress distribution. Some scientific models suggest that the SPA impact could have shifted the Moon's center of mass or altered its internal heat flow patterns, which in turn might have contributed to the differences in crustal thickness and the uneven distribution of volcanism between the two hemispheres. The thermal effects of such a colossal impact would have been immense, potentially influencing the Moon's internal temperature for millions of years, which could have affected volcanic activity and the evolution of its core. The scientific significance of the South Pole-Aitken Basin is multifaceted. Firstly, it serves as an invaluable window into the early solar system. Its pristine age and immense size make it a key target for understanding the nature and intensity of the late heavy bombardment. By studying the cratering record within SPA and on its rim, scientists can refine models of early solar system dynamics and the populations of impactors that shaped the inner planets. Secondly, as previously discussed, it offers unique access to the Moon's deep interior. Direct analysis of samples from SPA would be a scientific goldmine, allowing scientists to test theories about mantle composition and the Moon's differentiation. Thirdly, the basin encompasses part of the lunar South Pole region, an area of particular interest due to the confirmed presence of water ice in permanently shadowed craters. While the water ice itself is not a direct result of the SPA impact, the basin's geography means that many of these cold traps lie within its vast confines. This discovery has profound implications for future human exploration, as water ice could potentially be processed into drinking water, breathable oxygen, and rocket propellant, making a sustained human presence on the Moon more feasible. Thus, the SPA basin, with its potential resources and immense scientific value, becomes a strategic location for future lunar missions. Exploring the South Pole-Aitken Basin presents significant challenges. Its location on the far side of the Moon means that any lander or rover operating within it would face constant communication challenges, requiring relay satellites in lunar orbit to transmit data back to Earth. The rugged topography, with its immense craters, steep slopes, and deep shadowed regions, makes landing and traversing difficult for robotic missions. Despite these challenges, the scientific allure of the South Pole-Aitken Basin remains incredibly strong. The Chinese Chang'e 4 mission successfully landed its rover Yutu-2 within the von Karman crater, which is situated inside the SPA basin, in January of 2019. While not a NASA mission, its success demonstrated the feasibility of operating within SPA and underscored the global scientific interest in this unique geological feature. Future NASA missions, both robotic and potentially human, are eyeing the South Pole-Aitken Basin as a prime target for further investigation, including potential sample return missions that would bring actual pieces of SPA material back to Earth for detailed laboratory analysis. Such samples would provide unprecedented insights into the Moon's formation and the early history of the solar system, further solidifying the basin's status as a scientific treasure trove. The Great Basin continues to yield its ancient secrets to the relentless pursuit of scientific knowledge. Let us now, with the patience of our journey, turn our minds to the deepest geological secrets of the moon's secrets that were only whispered to us by the robotic probes and the first human observers. For a long time, the most profound puzzle of our lunar companion was not what was on the far side, but why it was so different. Why was the hidden face so rugged and heavily cratered, while the familiar face was a patchwork of dark, smooth plains and bright highlands? The answer, as revealed by decades of meticulous scientific exploration, is a beautiful and complex story of planetary evolution of a world that from its very beginning was fundamentally asymmetrical. It is a story of two halves of a single world, each following its own distinct path. When we observe the near side of the moon from Earth, we immediately notice two distinct types of terrain. There are the bright, rugged highland regions, which represent the oldest and most heavily cratered parts of the surface. And there are the dark, relatively smooth plains, known as maria, meaning seas in Latin, which were mistakenly thought to be bodies of water by early astronomers. We now know they are vast basins, filled with dark basaltic lava that flowed across the surface billions of years ago, creating relatively flat and less cratered expanses. While the near side certainly possesses a multitude of craters, especially in its highland areas, the presence of these extensive maria means that large portions of its surface have been effectively resurfaced, burying or filling in older impact scars. This geological activity has in a way smoothed out the near side over time, like an artist who paints over an old canvas to begin anew. In stark contrast, the far side of the moon presents a vastly different appearance. As revealed by the first robotic probes and later confirmed by human observations during the Apollo missions and by high-resolution orbital mapping from various NASA spacecraft, the far side is predominantly covered by heavily cratered highlands. It exhibits a striking scarcity of large maria. This means that the far side is saturated with impact craters appearing as an endlessly pockmarked ancient landscape. The density of craters on the far side is significantly greater than on the near side. Where the near side has patches of smooth dark mare, the far side offers a continuous unbroken canvas of impact scars, ranging from tiny pits to immense multi-ring basins. This visual difference is one of the most fundamental characteristics distinguishing the moon's two hemispheres, a great cosmic signature that tells a story of a world divided. NASA's scientific investigations, utilizing data from numerous missions, have provided compelling explanations for this pronounced asymmetry in crater density. The primary reason for the far side being more heavily scarred lies in the difference in crustal thickness between the two lunar hemispheres. This is a profound, almost unbelievable discovery. The moon, our ancient companion, is not the same all the way around. Detailed mapping missions, such as NASA's Lunar Prospector in the late 1990s and more comprehensively, the Lunar Reconnaissance Orbiter LRO, launched in 2009, have provided precise measurements of the moon's crustal thickness. These measurements consistently show that the far side crust is considerably thicker than the near side crust. On average, the far side crust is about 60 kilometers, or approximately 37 miles thick, whereas the near side crust averages around 30 kilometers, or about 18.5 miles thick. This dramatic difference has profound implications for the moon's geological history and its susceptibility to resurfacing events. The uneven distribution of crustal thickness is thought to have developed very early in the moon's history, possibly during its formation. One leading theory, the giant impact hypothesis, suggests that the moon formed from debris ejected after a Mars-sized body collided with early Earth. As this debris coalesced to form the moon, and as the moon subsequently cooled from a largely molten state, the lunar magma ocean gravitational forces and tidal interactions with Earth may have played a role in the uneven distribution of its crust material. The near side of the moon, perpetually facing Earth's immense gravity, was thinned out over time, while the far side turned away was left to thicken and harden. Another theory proposes that as the moon was forming, its internal heat was not uniformly distributed, leading to uneven cooling and crust development. Regardless of the exact mechanism of its origin, this crustal asymmetry has dictated the subsequent geological evolution of the two hemispheres. It's a story of a planet with a fragile thin shell on one side and a thick, impenetrable shell on the other. This difference in crustal thickness directly influenced the extent of volcanism. Magma originating from the Moon's interior finds it far more challenging to penetrate and erupt through a thicker crust. On the near side, the comparatively thinner crust acted like a weaker barrier, a kind of geological eggshell, allowing molten basaltic lava to ascend more easily to the surface through cracks and fissures created by immense impact events. These lava flows then spread across large basins, solidifying to form the vast dark maria that we see today. As these lava flows covered vast areas, they effectively buried or filled in many of the older impact craters that had formed in those regions. This process of volcanic resurfacing significantly reduced the visible crater density on the near side. In contrast, on the far side, the much thicker crust provided a more formidable barrier to rising magma. While large impact basins did form on the far side, such as the colossal South Pole-Aitken Basin, the subsequent volcanic activity needed to fill these basins with lava was much more limited. The magma simply could not easily reach the surface in sufficient quantities to create widespread mare plains. Therefore, the vast majority of the far side's ancient impact craters remained largely undisturbed by volcanic resurfacing. They have been preserved, accumulating over billions of years, giving the far side its appearance as a heavily pockmarked ancient landscape. It is a cosmic archive of impacts that has been left undisturbed for billions of years, a testament to a quiet, stubborn geological resistance. But there is a second complementary factor that contributed to the Moon's asymmetry, and one that NASA missions have also helped to identify. This is the uneven distribution of certain heat-producing radioactive elements within the Moon's crust and mantle. Data from Lunar Prospector's gamma-ray spectrometer showed a distinct concentration of these elements, specifically potassium, uranium, and thorium, collectively known as KEEAEP on the near side of the Moon, particularly within a region known as the Procellarum Creep terrain. These radioactive elements generate heat as they decay. Their higher concentration on the near side would have kept the underlying mantle warmer and more molten for longer periods, thereby facilitating the widespread volcanic eruptions that formed the Maria. The relative scarcity of these heat-producing elements on the far side meant that its interiors cooled more quickly, leading to less volcanic activity and, consequently, less resurfacing of its ancient cratered terrain. This uneven distribution of internal heat sources thus played a crucial role in shaping the distinct geological histories of the Moon's two hemispheres. The process by which NASA unveiled these fundamental differences involved a sequence of progressively more sophisticated missions. The initial visual confirmation of the far side's heavily cratered nature came from the Soviet Union's Luna 3, but NASA's own lunar orbiter program provided much higher resolution and more systematic photographic coverage. These detailed photographs clearly showed the prevalence of highlands and the scarcity of Maria on the far side, providing the first comprehensive visual evidence of the stark contrast. Following these visual surveys, later NASA missions employed advanced scientific instruments to quantify these differences. The Clementine mission in 1994, for example, carried a laser altimeter that precisely measured the Moon's topography, allowing for detailed mapping of the elevations and depths across its entire surface, including the far side. This data provided tangible evidence of the higher average elevation of the far side highlands compared to the near side. Lunar Prospector, launched in 1998, was instrumental in mapping the Moon's gravitational field and elemental composition. Its gravity mapping revealed distinct mass concentrations, or mascons, primarily associated with the large mare basins on the near side, which are dense lava flows. The far side, lacking these extensive mare basins, also lacked these prominent mascons, further indicating its different subsurface structure. Lunar Prospector's gamma-ray spectrometer provided the crucial data on the uneven distribution of radioactive elements, directly linking them to differences in internal heat and volcanism. The Lunar Reconnaissance Orbiter (LRO), launched in 2009, has arguably provided the most detailed and comprehensive data on the Moon's cratered surface and the differences between its hemispheres. LRO's Lunar Orbiter Laser Altimeter (LOLA) precisely mapped the topography of the entire Moon, producing incredibly accurate, three-dimensional models of its surface. This allowed scientists to quantify the depths and diameters of craters and basins across both sides, with unprecedented accuracy, unequivocally demonstrating the higher density of impact features on the far side. LRO's Lunar Reconnaissance Orbiter. Camera LRO has taken millions of high-resolution images revealing intricate details of individual craters, ejecta blankets, and the pervasive nature of cratering on the far side. The implications of these observed differences in cratering are profound for our understanding of lunar evolution. The asymmetry tells a complex story of how internal geological processes, driven by uneven heat distribution, interacted with external bombardment events over billions of years. The far side, with its thicker crust and lower concentration of heat-producing elements, essentially preserved an older record of the Moon's surface. This preservation makes it a unique laboratory for studying the early intense bombardment period of the solar system, known as the Late Heavy Bombardment. This period, thought to have occurred roughly 4.1 to 3.8 billion years ago, saw a dramatic increase in the rate of impacts on the inner planets and their moons. The far side's heavily cratered highlands provide a more pristine, less modified record of these ancient impacts, allowing scientists to calibrate models of cratering rates and to better understand the populations of asteroids and comets that pummeled the early solar system. It is a quiet ancient library of scars telling us a story that has been erased from our own planet's face, and so our quiet journey through the cosmic night draws to a close. We have drifted from the gentle gravitational waltz of tidal locking to the blurry, revolutionary first photograph of an unseen world. We have floated through the dreams of poets and pioneers, and we have soared with the human courage of the Apollo astronauts. We have touched down in our minds upon the firm ground of a silent world and have peered into the depths of its largest, most ancient scar, the South Pole-Aitken Basin. We have, in essence, traveled from an eternal mystery to a place of deep and profound scientific understanding. The Moon's hidden face, once a blank canvas for our imaginations, is now a portrait rich with detail, its story patiently, meticulously, and courageously unveiled by the restless spirit of humanity. The journey to unveil the hidden Moon was long and arduous. For millennia, it was a silent, unaddressed enigma, a philosophical challenge that defied our most powerful tools of observation. The true reason for its prolonged mystery was not a lack of curiosity, but the absence of a crucial technological leap, the ability to leave Earth's gravity and physically go there. This technological chasm meant that for centuries, the far side was not just hidden, it was fundamentally unreachable. The problem could not be solved by a more powerful telescope, a new kind of camera, or a more brilliant mathematician. It required an entirely new field of engineering, a new way of thinking, and a monumental collective effort that took centuries to build and a geopolitical race to ignite. The dawn of the space age, sparked by the launch of Sputnik 1 and the audacious triumph of Luna 3, was the moment this long-held dream finally began its slow, deliberate transformation into reality. The blurry images from Luna 3 were a tantalizing first step, a whispered secret that turned centuries of speculation into a single, undeniable fact. The far side was not a mirror image of the near side. It was a distinct geological entity, a heavily cratered ancient world that had been spared the volcanic resurfacing that defined its visible counterpart. This initial revelation set the stage for a new era of exploration, driven by an insatiable scientific curiosity and a national will to succeed. NASA's systematic and methodical approach to lunar exploration was a quiet marvel of engineering and scientific planning. The robotic scouts, Ranger Surveyor and Lunar Orbiter, were the silent pioneers who took on the riskiest first steps, meticulously gathering the data that was absolutely indispensable for the human missions that would follow. Ranger proved the ground was firm. Surveyor gently touched down to confirm its strength and composition. And the lunar orbiters meticulously mapped the entire world, including the hidden far side, filling in the gaps of the blurry Luna 3 images and providing the first comprehensive atlas of our lunar companion. They were the patient cartographers of a new world, a testament to how dreams are built, one careful, methodical, and technological step at a time. And then, of course, came the human gaze. The astronauts of Apollo 8 were the first to behold the far side, their journey turning a cartographical void into a lived experience. Their descriptions of a desolate, immense, and lonely expanse added a layer of human testimony to the scientific record that no robot could ever provide. The recurring communication blackouts that accompanied each pass behind the moon were a stark, powerful reminder of their profound isolation and a testament to the fragile yet powerful link that connected them to their home world. The unique solitude of the command module pilots who orbited the moon alone for days at a time provided an even deeper, more introspective look at this ancient world. Their observations adding a personal and philosophical dimension to our understanding. And the dramatic unplanned encounter of Apollo 13 with the far side, though not for science, underscored in the most profound way the immense distances and the critical importance of our fragile technological lifeline. The collective legacy of this long journey of discovery has been a complete transformation of our understanding of the moon. We now know that our lunar companion is not a symmetrical orb, but a world with two fundamentally different halves, a division written into its very geology. The far side is a cosmic archive, its heavily cratered highlands, a preserved record of the early violent bombardment of the solar system, a history that has been erased from our own geologically active planet. The reason for this asymmetry lies in a beautiful and complex story of planetary evolution. A thinner crust and a higher concentration of heat-producing radioactive elements on the near side facilitated widespread volcanic resurfacing, while the thicker crust and cooler interior of the far side left its ancient scars largely untouched. The South Pole-Aitken Basin, a colossal ancient impact scar on the far side, is a testament to the violence of the early solar system. It is a natural laboratory, a window into the moon's deep interior that has given us tantalizing hints of mantle material brought to the surface. It is also a frontier for future exploration, encompassing the permanently shadowed craters of the lunar South Pole, which are now known to harbor a hidden treasure water ice. This discovery adds another layer of profound significance to the far side, transforming it from a place of ancient history to a site of immense strategic importance for the future of human exploration. A potential source of drinking water, breathable oxygen, and rocket propellant. The far side is no longer just a place to look at. It is a place to go, to a place to build upon. The journey to unveil the hidden moon was a testament to the power of scientific inquiry and technological advancement, but it was also a triumph of the human spirit. It began with a quiet, inherent human desire to explore the unknown, a restless curiosity that has defined our species since its beginning. This journey has not just illuminated the moon, but our place in the cosmos. The image of a fragile blue Earth rising above the gray, desolate lunar horizon from Apollo 8 was not just a photograph. It was a moment of profound cosmic perspective, a reminder of our shared home and our place in the vast, silent universe. And so we have come full circle. We began by gazing at a single unchanging face in the night sky, a silent companion that inspired myths and legends. We now end with a deep scientific understanding of the moon as a complex, dynamic, and asymmetrical world. But in that understanding, we have not lost the wonder. Instead, we have deepened it. The The far side is no longer a void, but a canvas rich with scientific data and the promise of future discovery. It is a testament to how far we have come from simply dreaming of the stars to actively building the machines that can take us there. The moon is no longer a mystery, but a frontier. And in its quiet ancient silence, it continues to whisper stories of a violent, beautiful past and the promise of a bright, uncertain future. Let us hold on to this sense of wonder and carry it with us as we continue to gaze at the night sky, knowing now that there is so much more to see than meets the eye.